Physics. Okay, let's be honest. The word itself can sound a little intimidating, right? You think of crazy equations, super abstract concepts. But what if I told you it's not like that at all? What if physics is really just one single epic story? A story that connects something as simple as a falling apple all the way to the Big Bang itself? Well, that's the journey we're about to take. And this quote from Stephen Holzner just nails it. It might sound like a bit of an exaggeration, but it's really not. Physics is about, well, everything. It is the fundamental rulebook for reality. So in this explainer, let's peek inside that rulebook together. So where does a grand story like this even begin? Well, not in some fancy high-tech lab. Nope. It starts right here, right now, with all the simple things you can see happening all around you. And believe it or not, this is ground zero for all of physics. It's just the language that we as humans invented to describe motion. The moment you start asking simple questions like, hey, how fast is that ball rolling? Or where's it going to be in 3 seconds? And this is the most important one. Why did it start moving in the first place? That's the moment you start uncovering the universe's biggest secrets. That last question, the why, that's the one that changed everything. It's what led Sir Isaac Newton to realize that the universe isn't just random chaos. Not at all. It follows a strict, kind of beautiful set of rules that control all motion, everywhere. So rule number 1 is actually super simple. Just picture a hockey puck gliding on perfectly smooth, frictionless ice. If nothing gets in its way, it's just going to keep moving in a straight line at the same speed forever. It's not going to stop, it's not going to turn, unless some outside force, like, say, a goalie's stick, smacks into it. That's it. That's the universe's default setting. Things just keep on doing what they're doing. And the reason for that is a little something called inertia. Every single object that has mass has it. Honestly, you can just think of inertia as physical stubbornness. Yeah, it's an object's natural resistance to any change in its motion. So the more massive something is, the more stubborn it is, which means it takes a lot more force to get it to speed up, slow down, or change direction. And that idea leads us right to Newton's second law, probably the most famous equation in all of classical physics. It gives us the exact relationship between that force, the object's mass, and how its motion changes, which we call acceleration. It's beautiful, really. It means if you know any 2 of those things, you can always figure out the third.
And this slide just illustrates it perfectly. Imagine you're standing on a dock. You give a little dinghy a shove. What happens? It shoots away from the dock, right? That's high acceleration. Okay, now turn around and give that exact same shove to a giant oil tanker. It barely even moves. Its massive size means it has a ton of inertia, a ton of that stubbornness. So the very same force creates almost no acceleration. That right there is F equals ma in the real world.
Okay, so to apply all these forces and make things accelerate, you need something, right? You need energy. And in physics, energy has one golden rule. You can't create it, you can't destroy it. You can only change its form. Check out this little miniature golf loop. At the very bottom, as the ball is moving fastest, its energy is pretty much all kinetic. That's the energy of motion. But as it climbs up the loop against gravity, that motion energy starts converting into potential energy, which is just stored energy based on its height. At the very peak, for a split second, it's all potential. And then, as it falls, that potential energy turns right back into kinetic. The form of energy changes, but the total amount always stays the same. All right, so far, we've been talking about the visible world, pushing boats, rolling golf balls. But now, our story is about to take a turn and dive deep into a whole new realm, a world of powerful forces that you can't even see. For literally centuries, we thought of electricity and magnetism as 2 totally separate things. I mean, on one hand, you have the raw, scary power of a lightning bolt, and on the other, you've got the quiet, subtle pull that guides a compass needle. What could they possibly have in common? Well, it turns out, everything. Physicists discovered they were actually just 2 sides of the very same coin. And when you put them together, when these 2 invisible forces work in perfect harmony, they create something just absolutely incredible. You get light. Yeah, the very thing that lets us see the world is born from the dance of these 2 invisible forces. I mean, this is a huge moment in our story, where the unseen world of physics connects directly to our own senses. And speaking of light, it turns out that light itself was the key that unlocked the next totally revolutionary chapter of physics. Because once we understood what light was, this young patent clerk, a guy named Albert Einstein, he asked a really simple question that would completely change the world. Just thinking about that one question led him to his theory of special relativity. And let me tell you, this discovery didn't just update our old ideas about space and time, it completely shattered them. The answers he found are just as bizarre and mind-bending today as they were over 100 years ago. So here's the first wild thing he figured out. The faster you move through space, the slower you move through time, at least compared to someone who's standing still. And this isn't science fiction. It's a real, proven thing called time dilation. If an astronaut zipped past Earth at 99% the speed of light, for every 7 seconds that ticked by for us down here, only 1 single second would pass for them. It turns out time isn't this fixed, universal clock we all thought it was. And it gets even weirder. It's not just time that's flexible. Space is too. That very same rocket, to us, the observers back on Earth, it would actually look physically shorter in the direction it was moving. The actual fabric of the universe literally scrunches up for things traveling at these extreme speeds. And all of this led Einstein to his most famous insight of all. E equals mc squared. This little equation is so much more than just a formula. It reveals that energy and mass are actually just two different forms of the same thing. Mass is just an incredibly dense, concentrated form of energy. And the crucial part is, you can convert one into the other. And the amount of energy you can get out of even a tiny bit of mass is, well, it's staggering. Just look at our sun. It's basically a giant fusion reactor. To create all the light and heat that keeps our planet alive, the sun converts 4.79 million tons of its own mass into pure energy every single second. That's the power of E equals mc squared. Wow. Okay, so from a simple falling leaf all the way to the engine of the sun, this single story of physics has brought us an incredibly long way. And the final chapter, the one scientists are still writing right now, takes us to the absolute wildest frontiers of reality. And just look where these fundamental rules eventually lead us. Black holes, wormholes, the Big Bang itself, the idea that gravity literally curves the fabric of space-time. These aren't just separate crazy theories. They are the ultimate consequences of the same story we've been following all along, from a simple rolling ball all the way to the edge of the known universe. I mean, take a black hole. It's like the final dramatic encore for a really massive star. All of its mass collapses down into a point of almost infinite density, and that creates a gravitational pull so extreme that nothing, not even light itself, can get out. It is the ultimate expression of those rules of mass and gravity that we started with. And so, we end here with one last really big thought. Our journey has shown us that the things we thought were solid and dependable, like a fixed sense of space or a universal clock taking the same for everyone, they're illusions. So in a universe where everything is relative, where time and space themselves can bend and stretch, it leaves us with a pretty profound question, doesn't it? What then is our true measure? Maybe the only one that really matters is the one we create for ourselves.